Uh, as I said, the first aspect in speech is, of course, I am going to get the signal, right? So once I formulate a message, something is coming out of the mouth, which is in terms of compression rarefaction, and this will be a signal that is continuously varying in time, right? And therefore, we have to do some initial signal processing so that I can handle it using a computer, right? So, and computers can handle only numbers, right? They can only store finite bits. They have registers, memory locations where you store these numbers, and they also have finite precision because whatever it is, 64-bit precision. We have certain. It's not infinite, right? I cannot represent it to the I don't know, 10, what a zillionth kind of a, precision, right? Decimal place, correct? So, what are the basic aspects we do when we receive the speech signal? So, the first thing we do is something called sampling, right? Because as I said, we can only handle continuous numbers on the computer, and therefore, the first step that we do is actually take this continuous time signal, which I have drawn in blue here, right? And we take certain samples, usually equally spaced samples from it, right? We have a very simple idea like sample and hold. So this aspect is called analog to digital conversion. So we are converting the analog signal to a digital signal, and therefore we need this. I'm taking certain values in that continuous time signal. The blue curve is there, and I take certain values which are the red dots, right? Now, and for the purposes of this course, let us assume they are equally spaced, right? Now, one thing that will strike you is I am not taking the entire blue signal. I am only taking the dots, right? So there are places within the dots where it looks like we are not taking the information into account, right? So that is where there is a powerful theorem called the sampling theorem, which states that under certain conditions, these red dots are more than enough. These values of the signal at the red dots are more than enough to actually generate the original blue signal, okay? And that is the power of sampling theorem. And this is, of course, with the constraint of band limitedness and appropriate sampling frequency and so on. So this may have been covered in an earlier course, but if not, the most important thing to remember is that assuming it's a band limited signal, that if you sample it at twice the maximum frequency, this is of course assuming low pass kind of signal. For speech, it's mostly in the what's called the baseband. It exists up to about 7600 hertz, and therefore if you sample it at twice that frequency, that should be enough, okay? That greater than equal to comes because we are talking about pure sinusoids and impulses and so on, but for practical applications it should be twice the maximum frequency, okay? So that is the basic idea that you should take away from the slide, right? And more often than not, we do a pre-filtering so that it becomes band limited or almost band limited, and then we sample it at a certain rate, which is usually twice the maximum frequency. And obviously, because I am storing on a computer, I told you that it's only finite precision that I can handle, and therefore there's an aspect called quantization. So I am not taking the entire blue continuous time signal, but I am taking certain values of the blue signal that are usually equally spaced. How close or how far these values are depend on something called the sampling frequency, which you should remember, and usually it's twice the maximum frequency, right? And we will see in the next slide itself what that means. And second is the quantization aspects, because I have to store it on a computer as a number, so this number will always be with a finite precision. So in speech, there are two broad categories of signals we will deal with throughout this course. One is called narrowband signal or narrowband speech, and the other is called wideband speech, okay? So what does narrowband speech mean? This is speech typically that has gone through the telephone channel, okay? And many applications are actually going to be using the telephone channel, right? So of course the landline itself is the typical example, but all cellular technologies also operate in this bandwidth only, okay? So what does this mean? I'll explain to you. So if you look at the telephone channel, right, the telephone wire, right, this acts, and I'll come to this later, as a filter. Okay, what is a filter? I'll come in the next few slides. But basically, a filter is something that cuts off frequencies in certain bands and allows the signal to pass through certain bands, right? So the first, let me talk about wideband speech. So we humans, remember when I said when I speak, I move my mouth, jaw, articulators, and so on. So we produce frequencies from somewhere around 50 hertz all the way up to about 7500 hertz. Okay, so that's the range of frequencies that human speech exists. Okay, so these are the typical frequencies that we produce, unlike music, right? So even music we can produce higher frequencies, but again the ear, as I said, cannot hear beyond, like, say 20,000 hertz, right? So there's no point in having frequencies beyond 20,000 hertz because the human cannot hear it, right? That's a perceptual problem that I was talking about, right? So why deal with frequencies beyond that? So we don't even bother about frequencies beyond 20,000 hertz. But for speech, it's even more limited. I have to move my tongue, right? There is a finite, mass, so it takes some time for my lips, jaw, and also I cannot produce very high frequencies. So the maximum frequency that I produce is in the ballpark of around 7500 hertz, right? And the previous slide we told you that to sample it, I need twice that frequency. So I need to sample at the rate of 15,500, so approximately 16,000 hertz or 16,000 samples per second. That is what I am going to be sampling at. So that's called wideband speech. So this completely captures the entire speech signal with no aliasing or distortions. Okay, but when I pass it through a telephone channel, even though my original signal had signal frequencies up to about 7500, 7800 hertz, the telephone itself cannot handle frequencies beyond 3600 hertz, the telephone channel. Okay, so beyond that it cuts off all frequencies. So now you have the telephone channel acting like a filter. It does not allow frequencies beyond 3600 hertz. So when I speak, although I am producing frequencies up to 7800, when the receiver goes and then all this wire goes through, the frequencies above 3600 hertz get cut off. Okay, therefore from sampling frequency we know about 7200, but then we can have ideal filters. So we have about 8000 hertz sampling for telephone signals. Okay, so typically there are two broad ways that we handle speech signal. One is called the telephone speech, where we sample everything at 8000 hertz, and the other is the wideband speech, which is completely capturing everything. So when my microphone picks up, it's picking up everything, right? So if I record it at that particular point itself, then I will be sampling at 16,000 hertz. So these are the two broad things that you should remember. Okay, and of course we have to store this with finite precision. So normally we on a computer I have to store this 16,000 samples means I am essentially taking 16,000 red dots in the blue signal per second, which are equally spaced. Okay, but now this dot has to be stored on the computer, and the computer can only handle finite amount of finite precision, right? So normally in speech we use 16-bit PCM. This is for wideband speech. In telephone speech, there are standards that are already there, which are many standards, the European standard, the Japanese, the American standard. They are called A-law, mu-law, and so on, which basically optimize. I'm not going to go into the details. This reduce the number of bits, but the quality does not actually suffer. Okay, so that basically is the reason. So if you had 16,000 samples and 16 bits, so for storage or for transmission you need 256 kilobits per second, but we have this A-law, mu-law, which basically reduce it to about 64 kilobits per second. Okay, so which are without much loss in quality. So they are usually called toll quality, which is around later on we'll talk about something called the Morse score, how humans perceive the quality, and usually these are in the range of 3.8 to 4 Morse scores. Okay, now came another important idea, right? So this happened in the 1980s, and that is, as I said, we want to store speech efficiently and also transmit it efficiently along long distances. Okay, and in 1983-84, there was this scientist called Bishnu Atal, right? He actually grew up in Aligarh, and then he went to AT&T Bell Labs, right? He came up with this amazing idea of what's called code excited linear prediction. Okay, So this is the basic idea on which even today's communication works. So when I'm talking to you, whether on Google Meet or I am using any of the mobile phones, right, the voice technology basically is a variation of code excited linear prediction. Okay, and the basic idea in linear prediction is very simple, that if I observe the speech signal for about 10 samples, right, I can, to a fairly accurate level, predict the 11th sample. Okay, or if I have 16 samples, I can predict the 17th sample quite accurately. Okay, there are going to be some errors. Okay, and that is called linear prediction. I can predict the 17th sample by a linear combination of the previous 16 samples. Okay, and what are those coefficients of that combination? They basically later on can get converted to many aspects. One of them, of course, you can take them as it is, what's called the linear prediction coefficients. And in actual communication, when I'm talking on a mobile phone, it's actually surprising. It's not the actual voice signal that's going, it is these parameters plus some other additional information that is being transmitted. So it's actually not the voice signal that goes across, it is these parameters that are sent across the channel, right? And then in your mobile phone, it reconstructs the speech signal and it looks very natural, right? It looks as if your mother is talking to you or your father is talking to your sister or brother. It looks quite natural, and that is the power of the code excited part of it, which Vishnu Atal came up with. Okay, so we will deal with it a little more in greater detail later on. Okay, and again, we have standards for this mobile voice communication, right? So we have the GSM and the CDMA standards, right? And typically they operate in the range of about 7 to 13 kilobits per second, which is much lesser than the 64 kilobits per second that telephone kind of ELO kind of use, and much lesser than the 256 kilobits per second that we deal with. Okay, apart from this, these are for the speech aspects of it, but you know that music audio is also important aspects. So that's why typically you would have heard of the 44.1 and the 48 kilohertz. There we need to go up to 20,000 hertz, right? When you talk about music, the ear is sensitive to about 20 kilohertz, right? So and then we don't have ideal filters, and that's why double that frequency should be about 40, right? And so we have 44.1 and 48 as two popular standards. Okay, and then finally you would have heard of typically something called the MP3 players, which all of you use. These are lossy, and this is where I was talking about the perceptual aspects. The information that it loses, right? These you cannot construct the perfect signal that the speaker or the music was actually the signal was. MP3 are lossy, but the loss they introduce or the distortions that they introduce, right, is something that the ear cannot hear, right? So that is what is exploited. So MP3 player actually achieve what's called CD quality, right? For a human listener, it sounds as good as a typical wide 48 or 44.1 kind of standard, but it typically uses far less bit rate by exploiting the deficiencies of the ear, that certain things the ear cannot anyway sense, so we throw away all those information. Okay, so one of the important things you will see throughout this course, and this is typical of many sensory organs of the humans, is that humans are sensitive to frequencies, right? So two typical examples are the hearing and the visual aspects, right? So how do I see color? What is the color, right? Color is basically nothing but what? Frequency, right? And therefore I have in my retina these sensors, right? The rods and the cones, and these sense different colors or respond to different frequencies, and then the brain is, as I said, supercomputer sitting there that actually puts together all this information and makes sense of it, right? Similarly, the ear or the hearing mechanism is very sensitive to frequencies. So the message that I want to communicate here is frequencies, or the frequency play or the analysis of frequencies are going to play a very important role in this whole course. And so I'll spend a few a lecture or two talking about the frequency aspects of the speech signal, right? And how do we exploit them, right? And so first of all, we have to analyze what are the frequencies present in the signal, and that basically is going to lead to something called the Fourier representation, the Fourier series, the Fourier transform, right. So, I will typically be giving you some overview, but these are things that you would hopefully have seen it in some earlier course. Okay. So, just to give you an idea what is the whole thing is, you must have done also a course in linear algebra, right, or even in high school you would have seen this, right. So, if I have a point in a 3-dimensional plane, so this is a point in a 3-dimensional plane, right. So, here I have mentioned a point 3, 4, 2. So, because it is a 3-dimensional plane, I should have had the z axis also coming out, and so 3 units along the x axis, 4 units along the y axis, and 2 units along the z axis. And typically we use unit vectors, right, the I cap, the j cap, and the k cap, right. So, the point 342, which is a vector also, I can write it as a point or as a vector, is nothing but a linear combination of the I cap vector, the j cap vector, and the k cap vector. So, any point in a 3-dimensional space can be written as a linear combination of these 3 vectors. These are called basically the basis functions, right. And similarly, if I have a 4-dimensional space, I need 4 independent vectors, right, and I can write any point in the 4-dimensional space, which it's hard to visualize. But if you can, in a 4-dimensional space, I can have 4 vectors which are linearly independent, and I can write it as a linear combination of them. Or sometimes we prefer to have these orthogonal or orthonormal vectors, and that is why we do something called Gram-Schmidt orthonormalization or something, so that we have perpendicular directions for all the 4 vectors, right. Or if I want only 2 dimension, right, then I can talk about the x-axis and y-axis that are 90 degrees to each other, or any 2 vectors that are 90 degrees. These are also called orthonormal vectors for the 2D representation, correct. So, just like how I can expand a vector, right, if it is a 10-dimensional vector, I need a 10-dimensional space, so 10 independent vectors. Similarly, signals also can be expanded in terms of these basis functions, except the signal, if it is a function of time, I have to have other signals or basis function signals that are functions of time. So, I linearly combine those signals to produce a signal, okay. And this is where the beauty of Fourier analysis comes, okay. So, one of the things that Fourier said, that you give me a periodic signal, right, and one of Fourier's ideas, of course, this is under certain conditions, right. I mean, I am not going deep into the math. There are very important deep math aspects that I am brushing over, right. I am not even talking about it, but to a large extent, the idea behind it is that you give me sinusoids with different frequencies, okay. And if you give me all these sinusoids of different frequencies, right, I can add them up in some linear combination to get back the original signal. This is a claim made by Fourier, and at that point, right, because he is also talking about rectangular signals and so on, and so Laplace, Legendre, very big mathematicians at that time, were uncomfortable that because sinusoids are basically the sines and the cosines, they are extremely smooth signals, right. But these rectangular functions have discontinuities and so on. So, later on many other mathematicians explained and gave a deeper math basis to his claims, but by and large the people were even at that time not very comfortable with the idea that Fourier proposed, but it took some time for him to actually convince people that this can be done to reasonably, I mean, under certain conditions. And this is the basis of even today when we try to do Fourier analysis, right. We are trying to find out what are the component signals that are present that is used to construct. So, these are like the building blocks, the bricks from which you can construct any signal that you want, okay, under reasonable conditions, right. So, that is the basic idea of Fourier analysis. And so, by knowing what are the dominant frequencies, what are the frequencies that are present, I can do lots of wonderful things. I can compress, I can do so many things usefully once I do analysis of the signal, okay. So, but remember, I am starting with the same signal and I am just analyzing to find out what frequencies are present, right. The signal continues to be same, whether it is in the time domain or the analysis domain, which is the frequency domain, right. So, we talk about transforms here because it is transforming from the space of time to the frequency dimensions, right, frequency variable, correct. And therefore, this basically is actually the same information, but it is sometimes obvious, more clearer, either visually or otherwise in the time domain, and sometimes it's more informative or clearer in the frequency domain. The information is still there, but how it is visible, or how it is how can we easily extract this thing, it depends on sometimes whether we operate in the frequency domain or time domain, right? And once I talk about frequencies, you know that my eye, I just said, is sensitive to color. My ear, as we will talk in the next few slides, is also sensitive to ear. And so Fourier analysis becomes a very natural tool to analyze the frequencies of the speech signal, right? Because we said that frequency is a very important aspect. Okay. So, just to summarize, given these, there are many Fourier representations, actually 4 broad categories. So, one is what we call as continuous time periodic signals. So, this is the first thing that you would have encountered, and the basic idea there is that you will basically expand these periodic signals, right, in terms of sinusoids with different frequencies. And as shown in the figure, right, you can see that there are some sinusoids with different frequencies, and if you add them, we typically start getting back the original sawtooth, or the triangular, or the cosine, or the rectangular, and so on. Okay. So, Fourier operates in the analysis. We classify the different representations depending on whether the time domain signal is continuous or discrete, right, and whether it's periodic or aperiodic. So, you get, based on these time being discrete or continuous, and whether it's periodic or aperiodic, 4 different representations, right. So, the Fourier series is one of them. It's actually continuous time Fourier series. So, the signal happens to be continuous time periodic signal, from which we get the Fourier coefficients. Okay. So, if you look at the left hand side, this is what we are saying. So, f of x is a continuous time periodic signal, right. And just like basis vectors in that 3-dimensional problem that I talked about, this e to the power of I n x, right, basically these are the basis functions. They are functions in x, right, which we are going to take many of them, and their weights are c of n, which is nothing but our Fourier series coefficients. Okay. So, basically we expand in terms of these complex exponentials to get the continuous time periodic signal f of x. Okay. So, if you look at a transform kind of a representation, the input f of x is nothing but continuous in time and periodic, and the output, which are in this case a transform to the Fourier series coefficients, are discrete and aperiodic. Okay. And similarly, I can just, instead of having a continuous time curve, I can have a discrete time sequence, which is f of n, and same idea will happen, but now the variable from continuous time x has become a discrete variable n, and therefore the sequences is what we will talk about. E to the power of I omega naught k n, it is a sequence in n. Again, the ck's are nothing but the weights, the coefficients of the linear combination, and therefore the input now happens to be discrete and it should be periodic. Okay, that's a mistake. Okay, it should be what did they do? Discrete time Fourier series. Yeah, sorry, this should be discrete and periodic, and the output also will happen to be discrete and periodic. So, there is a mistake here. So, we should correct that to discrete and periodic, and output also is discrete and periodic. And in this case, you will see that basically both directions are discrete and periodic, and from that we will get something called the discrete Fourier transform, which is going to be the basis on which we do everything, right. A special case of that is called the discrete Fourier transform, and all computers we only do discrete Fourier transform. Okay. Now comes the, so let me take a break now. So, I will start from next class with what's called the Fourier transform, and we will start from there. Okay.